All right, so let's start. So let's start with the big picture. I like to say that the big picture is that there's interesting physics at all scales. What effective field theory lets you do is it lets you tease out this interesting physics at all scales. So you can, in particular, you can focus on a particular scale and find the interesting physics there using the tools of effective field theory. Now, that's a little different than how we teach physics. If you think about drawing a diagram from your freshman year to now many of you in graduate studies about how you learned physics, it was not by kind of focusing in on individual particular scales, but more from a kind of bottom-up point of view. So I would draw a picture of how we teach physics in the following way. So you start out as a freshman, you learn classical mechanics. You learn E&M, classical E&M. You learn Newtonian gravity. And then you build on these things. These things are your starting point, and then you build on them. So you learn quantum mechanics. And that builds on classical mechanics. You learn special relativity. Which is building on both classical mechanics and electromagnetism. At some point, you learn general relativity. And quantum field theory. And quantum field theory is synthesizing quantum mechanics and special relativity. And then these two here so you think about learning physics from the bottom up. In this picture, you learn these things first, and then you learn these things, and you sort of keep synthesizing, keep putting things together. We're going to be doing in this course the exact opposite of that. We're going to be taking one of these blobs, in particular this one, and we're going to be looking deep inside it, trying to make more and more specific field theories. So if you want to draw it as a blob, we'll be taking quantum field theory, and we'll be looking for derivatives of it, or perhaps derivatives of it, like this, and figuring out how to take a very general theory, like quantum field theory for the Standard Model, and finding things that are more specific and more, in some ways, more powerful than just having the original theory we started with. More powerful in the sense of being able to do calculations. So why do we want to do that? There's a couple of different reasons. Or why do we do that, since, as I've tried to convince you with the outline of the course and some of the presentation topics, that this is something that happens all over the place. So as you go up in this chart, it actually becomes, even though you have a more general theory and it becomes more beautiful and you can write down synthesis of physics in fewer lines, it also becomes harder to compute things. So just as an example, if you just wanted to compute the energy spectrum of hydrogen, and you know very well that you can do that in quantum mechanics, and it's a classic example and fairly easy. If you try to do that in quantum field theory, it's much harder, because quantum field theory in some sense has too much for that problem. So that's one example. Another is the elliptic orbits of the planets, which are easier in Newtonian gravity than in general relativity. And these are just two examples. There's many more where the field, one of these blobs may be too general for actually tackling the problem that you want to deal with. And by focusing in, which is what effective field theory allows you to do, you can get more ability to compute more accurately and in a simpler fashion. So what we want when we think about effective field theory is we want the simplest framework that captures the essential physics. We don't want to carry along for the ride a whole bunch of superfluous things that are not important for the problem we're trying to deal with. But we also don't want to give up anything. So we're very demanding. So even if we're giving up something in our leading order description, we want to retain the ability to correct that leading order description order by order in some expansions so that we can make it as precise as we desire. So I'll say that we can correct it in principle to arbitrary precision. So if you like, what we're doing is we're taking quantum field theory and we're expanding it. And the lowest order term in that description is an effective field theory. And that effective field theory may have different fields. It may have different symmetries. And it will certainly have ability to calculate in a different fashion than the original theory. But we will keep other higher order terms in that expansion, and therefore we'll be able to correct it to arbitrary precision just by expanding to higher and higher order. So examples of this that even are familiar here: non-relativistic expansion, getting back to non-relativistic quantum mechanics, or doing a post-Newtonian expansion in general relativity to go back towards Newtonian gravity. You don't have to stop at the first term. You can keep higher order terms. And in that way, you could calculate, for example, energy levels in hydrogen using a non-relativistic framework that encodes all the ingredients of quantum field theory. Or you could use, you could look at the orbit of planets and relativistic corrections and general relativistic corrections by expanding this theory. So those are two examples. So most of the examples that I've listed on the project list are of the type of taking quantum field theory for the standard model. Some of them involve gravity, but most of them involve the standard model and expanding it and focusing in on particular degrees of freedom. So let's say that we've picked a physical system and we want to describe it. What are the things that we should do in order to develop an effective field theory? What are the steps? So the first thing you need to do is figure out what the relevant degrees of freedom are. What are the things that actually matter for the problem you want to study? Sometimes that is easier than other times. Sometimes it's completely obvious. You want to study some low energy properties of the standard model. You get rid of the heavy particles. You keep the light ones. Fairly straightforward. Other times it may be tricky to actually determine what the relevant degrees of freedom are. And people in the field may even argue about what they are. So we'll talk about examples of both types here throughout the course. So it sounds trivial, but it may not be. You also want to think about the symmetries. Sometimes that guides you in thinking about the relevant degrees of freedom. Sometimes these things go hand in hand. But that's certainly an important ingredient in developing the effective field theory. And you also have to be careful here, because sometimes you might have a theory that has no symmetry or doesn't have an apparent symmetry. But when you start expanding, which is what I've argued you're going to be doing, when you start expanding, you may have a symmetry suddenly appear. And we'll actually talk about several examples of that happening throughout the course as well. So your effective field theory may have more symmetry than the theory you started with. Because you've neglected something, you could have more symmetry. And the other important thing is to figure out what you're expanding in. And at the same time, what the leading order description of the theory is. What is the lowest order Lagrangian? And basically, these are the things you have to do to get started. If this is true, actually, independent of kind of what theory you're talking about, if you're doing quantum field theory, what this first one means is figuring out what fields you're going to be using. The symmetries basically is guiding you about the interactions. If you have gauge symmetry, then of course you're going to write down something that respects that symmetry. That's going to tell you something about the interaction terms. And then finally, this expansion parameters goes under the rubric of what is called power counting. And if you take those three things together and you figure out the leading order description, then you have an effective field theory. You write down a Lagrangian for it. Should try to use some color. So if you thought about regular quantum field theory, for example, for the standard model, you'd also do these first two things. You figure out what the fields are, you figure out what the interactions are, but you don't think about too much about this question, about the power counting. And actually, more broadly, in the field of effective field theory, this idea here of power counting is very important. It's as important as something like gauge symmetry. Okay? It's really a fundamental thing about the whole framework that you're doing. So in an effective field theory, the power counting is just as important as figuring out things like symmetries. And in particular, just to make it sort of clear that it's important, I'll compare it to gauge symmetry. It's really a fundamental ingredient in what you're doing and in the whole theory. Because the power counting being consistent is actually necessary for the whole field theory, effective field theory, to make sense. OK, so what's the key principle? Well, there's a key principle of quantum field theory that we're using when we design effective field theories. And that is that we're insensitive to physics at higher energy scales. So going back to Wilson, if we're interested in describing the physics at some scale m squared, we don't need to know the details of physics at higher energy. So at scales lambda squared that are much bigger than m squared, we don't really need to know the details of the dynamics that are going on there. We don't need to know the field content necessarily at those scales or anything else about the dynamics. And that is, in some sense, a key idea that makes the whole idea of effective field theory possible. I want you to make sure that you don't think of this too narrowly. In the way that I've written, it's actually a little bit too narrow, because I said that I've described it in terms of mass scales. So I've kind of intuited into your mind something like a Z boson or a W boson, which is a heavy particle from some perspective. And maybe I treat that as a heavy particle, and I'm interested, let me say it differently. Say I'm interested in a light particle like the bottom quark. Then I can get rid of physics at a heavy scale like the W mass. Or if I think about how new physics impacts precision electroweak data, and that new physics is heavy, then I can think about effective operators. That's kind of the intuition I've given you with the sentence that I've written here, but it's actually that's not quite general enough. And the reason it's not quite general enough is that this mentality doesn't always apply just strictly to mass scales. If I say this, m squared much less than lambda squared, then you immediately think that you're expanding in m squared over lambda squared. And that, of classic effective field theory, that's exactly what you do. You expand in light scales divided by heavy scales. They're mass scales. They're invariant masses. They're Lorentz invariant quantities. That's the most common thing that you do. We're going to be doing much more than that in this course. We'll be talking about cases where the power counting is in situations that are not simply m squared much less than lambda squared, but other things, dimensionless parameters. So sometimes it will become more complicated, but still this guiding principle that there's physics that's far away in some sense from the physics that you're interested in, that it can be removed from the theory when you're just talking about it. In that sense, this is more general. That it's really not just a strictly one-dimensional thing as it would be if I describe it in terms of mass scales, but a more general principle. And I think that'll become clearer when we actually do examples where it's not simply mass scales. We'll, of course, start out by talking about mass scales, since that's the classic thing that most people think of when they think of effective field theory. So can anyone give me an example? Just try to get the class engaged here. Can anyone give me an example of an effective field theory that doesn't involve expanding strictly in mass scales, that involves some other type of expansion?